the next talk of this morning session. Starts now, and the speaker is Ole Warnaar, another speaker who does not need any introduction. Ole, please go ahead. Actually, he's here. Yeah, you discuss Koornwinder intervals.
Actually, I promised Dick to wait, but he's not here.
Ah, you promised Dick to wait, but you cannot do so because.
I cannot do so, no. So let me start by thanking the organizers for inviting me and giving me a chance to speak. And Dick's still not here, so I better get going. So, all right. So, what's virtual Koornwinder intervals? What are they about? Well, before I start, I should say this is all based on joint work with Eric Rains from Caltech. That's Eric when we're visiting Australia. A nice Australian hat. And all right, so well, we've seen this many times before. I'm going to talk about partitions, ordinary partitions, plane partitions, and things related to that. But my approach is going to be quite different to the usual, I guess, Q-series approach. So I hope I'm not alienating most of the audience for what's coming next, but I'll definitely get back to actually the problem of counting partitions. But I'm going to take an approach based on representation theory. Okay, so we want to count partitions, but rather what I'm going to do first, I'm going to count multiplicities occurring in representation theory. There's many ways in which multiplicities can occur in representation theory. Probably the best well-known is, for example, if you take tensor products of irreducible representations and you decompose this into irreducibles, you may ask yourself, well, how often does a particular irreducible representation occur in some tensor product? We'll give you a number, and we call that number a multiplicity. That's just one example. And in this case, for example, if you consider GLN, you get the famous Littlewood-Richardson coefficient, that many of you may have heard about. But I'm going to use a slightly fancier or perhaps a slightly simpler, depends on your point of view, of a notion of multiplicity, because the kind of numbers, and maybe you missed this, but this is the 0-1 of counting, because I'm going to look at the situation where the numbers I get only can be 0 or 1. Okay, so again I need a little bit of notation, so let G just be your favorite compact group, and if you're not a group theorist, it's good enough to you can think of the circle, for example. Okay, or the torus, or perhaps UN, and by N, unitary matrices. So these things are not that complicated. And now we have you've chosen your favorite group, and now you pick a compact subgroup, H, and we call this group G together with H a Gelfand pair, or the subgroup itself a Gelfand subgroup. Well, so we get some technical condition. Namely, if you take an irreducible representation, rho in V, so V is sort of the space on which we're acting, then the subspace that's left to the H-invariant subspace must be at most one-dimensional. So it seems like a rather technical definition. So loosely speaking, what this says, if you take the trivial representation of H and you now induce to G, then you want that is, in this induced representation, this trivial representation occurs at most with multiplicity 1. So again, we have numbers that can be at most 1. All right.
Why do you have the strict inequality there?
Sorry, where do I have the strict inequality? Oh, this, I would rather here is a, I should definitely add the equality sign here, because this will be extremely boring. So we can just the 0 of counting rather than the 0-1. So thanks for pointing out that typo. All right. So, as I said, from the point of view of partitions, this may perhaps seem a little boring, because the only numbers you can ever get are 0s and 1s. And you'll never get to Krishna's favorite sequence of numbers. Clearly, they go up to numbers that are bigger than 1. Okay? Everyone recognizes these numbers. We've seen them before. No one?
Aren't they Rogers or Monaghan?
I believe so, unless George is shaking his head, so maybe there's a little error in something. We're supposed to to be the number of partitions satisfying the difference two conditions. So these are the two Rogers or nitrogen partitions, or the number you get, but obviously I made some errors here. So how you can get to these numbers when you only count zeros and ones? Well, that's of course because the actual dimensions of the representations I'm concerned about, they themselves can be higher dimensional, so we can still get some meaningful counting going. All right. Well, so back to these Gelfand pairs. So, well, in fact, back to the more general situation, that if we have some locally compact topological group, and again, if you're not familiar with this, just think of the reals, then we all, I guess, know there's this unique measure called Haar measure, for which the action of the group is left invariant, and in particular, if the group is actually compact, it's sort of an if and only if statement, then we have a unique measure that we can normalize to be exactly 1. Okay, and so we're interested in this Haar measure, and we're interested in integrals over the group with respect to Haar measure, and typically we don't actually indicate the measure, so we just write this as integrals like this. And I'm only interested in functions that are, well, we call them class functions, so they're functions that are invariant or they're constant on conjugacy classes. Okay, so it's a particular class of functions. We can look at more complicated examples, but this is the simplest example. All right, so for example, if you just take that function to be just the product of two characters of irreducible representations, then we know that, well, these characters, they're just orthonormal with respect to the Haar measure. That's a standard result from also classical group theory. But I was interested in these Gelfand pairs, and so now we're not integrating over the full group, we're only integrating over the Gelfand subgroup, and we just take a single character rather than the product of characters. But essentially, if you take this character over here and you expand this in terms of the characters of H, so this is not going to be irreducible with respect to H, but we know that the trivial representation occurs at most once, and so therefore, this integral here either gives you 0 if the trivial representation doesn't occur, or 1 if it does. Okay, so this particular integral here is either 0 or 1. So let's do this for an example. And the example I've chosen is the Gelfand pair GLN UN. And I should point out this is with respect to the quaternions. And so there's a whole list of Gelfand pairs. They have been classified, so you can just look them up. And this is just one example. This is going to be my example for today. And, well, many people will know the characters of GLN. They're known as the Schur functions. So in other words, I'm just integrating a Schur function with respect to, well, this Gelfand subgroup, which is isomorphic to just the symplectic group. You have to be a little bit careful, because when you say symplectic group, you have to tell people what symplectic group you're talking about. We need to be compact, so this is, in fact, what is known as the compact symplectic group, because a generally standard symplectic group over the complex numbers is not actually compact. All right, so here we have a nice integral that we know is either 0 or 1, and it turns out it's nearly always 0 except when the partition labeling my Schur function, so labeling my irreducible representation, if I say lambda prime is even, it means that the columns, if you draw the Young diagram of this partition, all of the columns must have even length, otherwise you get 0. Okay. Oops, that's too quick. So, well, then there's another little bit of sort of standard theory that rather than integrating over the full group, it's enough to integrate over a maximal torus, that's sort of a maximal deviant subgroup. And what it does to your integral, well, you get a normalizing factor, which is essentially determined by the dimension of the underlying ground group of your group G. And your integral picks up a Vandermonde type determinant. So this is the Vandermonde of type G, where G is your your corresponding group. Okay, and so we go back to what we had over here. Rather than integrating over all of the symplectic group, all I need to do is integrate over a maximal torus. Okay? So if I do that for the previous example and explicitly sort of get rid of all of the group theory notation, you get a very, very explicit integral. Okay, so this was already known to a while, so this is an old result. Okay, so you have an Assure function on the left, and this x plus or minus 1, this means it's on n or on 2n variables, but each variable occurs together with its reciprocal. And then you have these products over there, which are just coming from the Vandermonde determinant squared, and this equals 0 or 1. So you can actually just put this on your computer and try this for low-rank cases. You can just, or you give it as an exercise for your students. It's quite a fun integral trying to evaluate this. Okay? All right. So where's this all going? Well, I need a little bit more. And so now I need to tell you what a virtual Koornwinder integral is. So first of all, I need to tell you what a BCN symmetric function is. So we all know what a symmetric function is. It's just a function that's symmetric on the permutation of the variables. BCN symmetry means that you're symmetric under the action of the, well, the group signed permutation. So if you take a variable and you take its reciprocal, replace it by its reciprocal, then your polynomial or your function is still invariant. So here's a little example. You know, check this. If you replace the variable x2 by its reciprocal, this thing won't change. Okay, and so we're interested in the space of BCN symmetric polynomials. And in particular, the top degree is just the space of symmetric polynomials. All right, so on that space, I'm going to consider what is known as the Koornwinder density, and the details are not important. It's just a bunch of infinite products, and we've seen many infinite products during the week. The only thing that's important is contains quite a few variables, so this T bar here is just a collection of T0 up to T3, and then there's a Q and a T as well. So this is some complicated sort of weight function, if you wish. But I should point out that this includes exactly this product we had in Weyl's integral earlier, if you choose your T0 up to T3 in the right way. So this is something that includes what we saw in Weyl's integral coming from these Gelfand pairs. But it's more general. Okay, and then we can use this Koornwinder density to define an inner product on the space of BCN symmetric polynomials. And essentially the Koornwinder polynomials, that's why these densities called the Koornwinder density, they're functions that are orthogonal with respect to this inner product here. Okay, so there's a unique family of orthogonal polynomials that sort of are orthogonal with respect to this Koornwinder density. And then there's some normalizing techniques, so the leading term is a certain BCN monomial symmetric function. Doesn't really matter what it is. Okay, so that's the Koornwinder polynomial. And I already mentioned the top degree term of a BCN symmetric function is a symmetric function. So if you take the top degree term of a Koornwinder polynomial, you get another famous function that's known as the McDonald polynomial. And the McDonald polynomial is a generalization of the Schur function that we saw earlier in Weyl's integral. All right, so we've got all that, and then finally I can define what a virtual Koornwinder integral is. It's just you take the function and you integrate it with respect to this Koornwinder density, and then you normalize it. That's not so important, and that we call this a virtual Koornwinder integral. Why it's called virtual, I don't have time to explain. There's a connection with what are known as virtual Koornwinder polynomials, and that's where this name comes from, but I have no time to explain it. All right, a little bit of combinatorics now. So this is fairly similar to what Richard Stanley did just a few talks ago. So if we take some Young diagrams, I'm not going to consider hoop length I'm actually going to consider arms and legs and co-arms and co-legs. So you take a box, and all of the boxes to the right, we call that its arm. So here we have an arm of length 4, a leg of length 3, and then the co-length, they are both 2, because that's the number of boxes above or to the left of a given box. So here, as I said, 4, 3, 2, 2. And you can do this for every box in your Young diagram. And so this is an integral that was proved by Eric Range a few years ago. And this is a QT analog of Weyl's integral coming from the Delphine pair. Okay, so now we have a Q and a T. You see on the left we have this virtual Koornwinder integral with respect to the McDonald polynomial. And again, it's almost always 0, except when our partition has all its columns are even. And then you get this function b, and this function b is just a, well, you can either say this is beautiful, or you can say it's complicated, but it's completely factorized, and it's all in terms of these combinatorial arms and legs. And in particular, when q is equal to t, this becomes 1, and you get back actually Weyl's integral. Okay? So this is also fairly deep. This is very hard to actually prove, unlike Weyl's theorem, which we nowadays think of as easy. Alright, so now I need to get back to counting things. There's one last little ingredient I need, and then I've got everything to do some actual partition theory. And that is a formula which allows me to expand the Koornwinder polynomial, labeled by rectangular partition. That's what this n to the power n means. I multiplied by little monomial, so now it becomes a symmetric function. I can expand this in the McDonald basis, because they're basis for the ring of symmetric function. And what we proved is that the coefficients in this expansion are precisely given by virtual Koornwinder integrals. Well, so what? Sorry, that's another alphabet. I'm expanding a Koornwinder on x in terms of a basis, also on x, and I'm saying the coefficients, these get integrated out. Okay, so that's, yes, it doesn't depend on y. This is an integral you need to perform, and they are the coefficients. Alright, so as I said, we now need to get back to partitions. So the example I've chosen for today is, well, I have two examples. The first is symmetric plane partitions. Okay, so plane partitions are just stacking of cubes like this here, or if you wish, you can draw this as a Young tableau. So the number 4 just means in the center I've stacked 4 cubes, and then I've got 3 to the right of that, so that's 3 and so on. You can see the correspondence. And in this particular case, I've chosen symmetric plane partitions, so if you reflect in the main diagonal, the numbers don't change. And the numbers on the main diagonal, the 4 and the 2, they're all even. Okay? This is a particular class of plane partitions, and there's a beautiful formula. Try to compute the generating function of these symmetric plane partitions such that the main diagonal, so the number of boxes on the main diagonal is even. We get this beautiful product formula. So again, not of taste, but I think this is very pretty. So how can we understand this using sort of the machinery I've just developed? Well, so I take my symmetric plane partition, so I take a different one here. So that this is still a symmetric plane partition, and here is its representation in terms of the stacking of cubes. And this is an idea of Kunkov and Reshetkin. So what they did is they read this partition with what they call diagonal slices. So you see a 4 and a 2, and then you see a 2 and a 2 and a 2 and a 1, and so on. I'm losing my mic. And each of these slices is itself a partition, just an ordinary partition. And now what they do is they reassemble these slices, and why do I write squares here? Because it's symmetric. So apart from the main diagonal, all these slices occur twice. So I have 2 of these 2 2s, 2 of these 2 1s, sort of on opposite sides of your main diagonal. And now I build a new partition. I start with my 4 2, and remember these numbers are even necessarily. So this shape here is 4 and a 2. This is an even shape. And now I take my 2, 2, and I just put this on top of this. But I have 2 of them, so I do this twice. So here's my 4, 2, and I put those on top of this. Now I take this 2, 1, I stack this on top of this, but again I do this twice. And then I've got the 2 and the 2, I put it on top, and then finally I've got this really sort of skinny kind of partition. So what can we observe about this thing here? Well, first of all, that the shape is even, that's the 4, 2, and then all these numbers in here, they're odd. Because we stack 1 layer and then 2 layers every time afterwards, so all these numbers must be odd. Alright, but we can exactly enumerate these things, because this is, we know that this is precisely enumerated by sure functions. And it's precisely enumerated by sure functions, where as variables we take odd powers of q. Okay? And we're summing over all partition shapes, that as I said, this partition must be even. So we have something even on the left, and it's still this nice product. So that's what we need to prove. And so the thing you should note here, if you read this formula from right to the left, we have this nice infinite product. We expand this in terms of these sure functions, and the only partitions that occur are when the partitions have even shape. And this should remind you of Weyl's integral. He only had partitions, well, rather than even rows, he had even columns, and that's just a matter of taking the conjugate. So you should think this is Weyl's integral, somehow. But how? Well, instead of this top formula, what we do is we just say this is a special case of something much more general, rather than a sure function where all the variables are powers of q. I just replace them by the actual variables x, where now x is not specialized, and my plane is on the right-hand side. This is precisely one of these Koornwinder polynomials. Because we know if you take a Koornwinder and we take these geometric progressions, it precisely gives you that product. So what we need to prove is that this Koornwinder polynomial expands in terms of sures, just like this. Well, but we had a formula that said how we would expand Koornwinders in terms of McDonald's. That's when you have a q and a t. Here the t is equal to q. And so it's precisely our theorem with t equal to q and a special choice for all of these t0 up to t3. And therefore, this follows if you can show this virtual Koornwinder integral, which is nothing but Weyl's original integral. And that's the proof, or the take-home message is, if you want to prove the Proctor's-Tenbridge plane partition theorem, well, it's really nothing but Weyl's vanishing integral, which is really itself nothing but taking the Gelfand pair, and that's it. So these statements are all completely equivalent. And of course, they all live in very different mathematical worlds. One is the world of the Gelfand pairs, and the other is the world of plane partitions. But essentially, these things are the same. So it's quite surprising, but it's a neat connection. All right, time for one more example, because I need to get back to these Rogers-Ramanujan partitions. Can I get them in the same way? And so the answer is yes. In fact, I can get a lot more. So in recent work, I think it's about to appear, I haven't seen it yet, with Ken Ono and Michael Griffin, he's still in the audience. We generalized the Rogers-Ramanujan identities to much more general products of theta functions. So again, I don't have time to explain the full details, but you see a sum side, which I've written in a very neat form by sort of hiding everything that's going on. It's just written as a whole little polynomial, which is a special case again of this McDonald polynomial. But it's just a q function that completely factorizes. And on the right, you get this massive product of theta functions. If you take m and n, so here are the two free variables here, to be equal to 1, this identity is precisely Rogers-Ramanujan. If you take n equal to 1, and you take larger values of n, this is precisely the Andrews-Gordon identity. Okay, but as I said, this is much more general, and it's related, as you can see, to affine Lie algebras, again, I don't have time to explain how that arises, but this is a specialization of character of that particular twisted affine Lie algebra, and so the sum is equal to a product. Again, how can we prove this? And how can we prove this in a more efficient way than originally done, I guess, by Michael, Ken, and myself? Again, you notice that on the left-hand side, you see a sum over partitions, and the partitions have to be even. So again, if you think this comes from some vanishing integral, because most partitions don't occur. This is again this sort of 0-1 counting that we're doing, and so here's in fact the second identity, which is very, very similar. And so here is how you prove this. You simply take, again, the theorem that we had that said that the expansion of a Koornwinder in terms of McDonald polynomial is given in terms of a vanishing integral. You take Raynes' vanishing integral, now the full QT analog of Weyl's integral. You take a limit, and that limit is R here is essentially a Koornwinder times a monomial. Again, we specialize all these T's that we had all to 0, so it's a very simple special case. And we take a limit, and lo and behold, on the left-hand side, you get this beautiful theta product, because these Koornwinder polynomials, if you take these geometric specializations and then take a limit, it turns into a product, and on the sum side, you precisely get what follows from our theorem, and we have a very easy proof of not just the Rogers Ramanujan and the Edwards Gordon identities, but this much more general family of identities related to affine Lie algebras. And that's where I should start.
Questions, comments?
What exactly do you mean that a very easy proof?
Well, okay, a very easy proof assumes some very deep results. So, for example, Raynes' QT analog of Weyl's vanishing integral. Unfortunately, we don't have a QT theory of Gelfand pairs. That would be really, really cool. If you could simply find some underlying group theoretic reason why that more general QT vanishing integrals should exist. It was initially conjectured by Eric and then later proved, and this was really, really hard work. So yes, of course, it depends on one's point of view, but once you have that, I would say this is a very elegant, it's at least an elegant approach. Illuminating, okay, I'm happy to accept that.
Other suggestions will come.
So are you multiplying the bottom two lines, or they are separately?
These bottom two lines is something you don't see in the ordinary Rogers Ramanujan or Edwards Gordon identities. So here we have two variables, n and m. N is sort of the rank of your Lie algebra, and m is the level of the representation. It turns out you have a beautiful level-rank duality, because if you interchange m and n, you can see nothing happens. So rather than say this comes from the twisted affine Lie algebra A to n, you can also say it's A to m, but then of course the representation would then be, you would have to take a different representation of that algebra. So you see some beautiful dualities coming here in that you don't see if you only look at the one-dimensional subfamily of this, you don't see it. So that's what this is.
So you have showed the plane partitions where we have evens on the diagonal, and do we know anything else about any other arithmetic progression on the diagonal? Do we know odds? Do we know
there's many more theorems for plane partitions. For example, McMahon's original conjecture that was simply symmetric plane partition, so he wasn't demanding that you had evens on the main diagonal. There's again a beautiful formula for that, which George is one of the provers of that. And you can prove this in a similar way like this. It's just you need another Gelfand pair for it, and I only wanted, I had 30 minutes. But certainly,
You want with odd numbers?
odd numbers on the main diagonal, I'm not sure if people have considered that. So not every, sorry? Numbers, not, look, you can, no. I mean,
Like, do we have a product representation for those two?
all
That's
the
like, well,
products, no. I mean, in general, if you cook up something random, it won't have a nice product form,
yeah,
unfortunately.
sure.
Maybe one more suggestion? To order? No one dares now. Okay. Then this finishes this part, so thank you all for your